Yeah, hello. Good evening, everyone. Am I audible?
Yes, good evening, sir.
Okay, thanks. Okay, so the current week is week 8. So I hope you have started watching. So today we will discuss the week 8. Before starting the session, if anyone have any specific query in week 8 or any other query, okay. So no response. Okay, so then I'll start with the all content summary.
Hello, sir.
Yeah, Priyadarsan.
Sir, can you explain that pre-order and post-order transfers, sir?
Pre-order and post-order. Okay, this is from previous weeks, na? Okay. Mhm. So you are asking only order or any other thing related to this? How to generate order or like?
Both, all things included, sir. Related to that pre
Pre,
and
post.
post-order.
Okay, fine. Okay, so let me clear this, then we will move to the week 8 content. Let me share my screen. So, first thing is this pre-order, in-order, and post-order. All these three are traversal algorithms. So that actually the task for this is. Okay, someone said finding closest pair part. Okay. So we will also cover this. Okay, so regarding this tree traversal, so we have some tree in the input, and we want to traverse all the nodes of the tree. So how we can traverse? So there are three algorithms we have, three different way we have to traverse the tree nodes. So first is called in order, and another is pre-order, and another is post-order. Okay, so actually all algorithms traverse the nodes. So traverse, or you can say just visit all the nodes. So what is the difference between this in order and pre-order? Let me just give me 2 minutes. Yes. Okay. So suppose we have one tree. So I'm just creating some random tree. So like A, and this pre-order, post-order, this these traversal can work on any normal tree also, normal binary tree also. So not only for the binary search tree, because binary search tree is also a binary tree. So like B and C, D, E, F, G. Okay, so I've created this one binary tree. Okay, so how the that so first thing is in order. Okay, so in order, and another is pre-order, and another is post-order. So all these three, we use the recursive way to visit all the nodes. Okay, so we start from the root node, but after that, because we have left child, we have right child, there also be a possibility that if any node have only one child, or leaf node doesn't contain any child. Okay, so recursively we checks, if we have left node, then we will move to the left node. If we have right node, then we will move to the right node. So generally we call the same recursive function to the right or left childs. But how, what is the order of actually we used it, okay, in these three algorithms? So that is the important. So in order algorithm, we used this is the current node. So generally if we are at any node, so we can say that we are at current node, and from current node, so what is the next step? So in order traversal, our task is, first we will, in the first step, we will call our same algorithm. So suppose this algorithm is calling on the current t node. Okay, so I'm just giving the t as a current node. Now the first step will be the call the same algorithms in order algorithm on the T left child. Okay, so this is the first step. So this is a recursive call. This is a recursive call, and this recursive call we are calling on the left child of T. Okay, and second step is visit the node. Okay, so visit the current node. Current node T. Okay, so we are just we are at actually current node T, so we are just visiting the current node. So visiting means you can print or you can do some operation on that. Okay, so any things you can perform in this step. Third step is again a recursive call. Okay, so this is in order, and this is on right child. Okay, so we are just assuming that each node has the left field and right field. So left field contain the address of left child, the right field contain the address of right child, or some data field, so that contain the data, current data, so that we can print or we can do some operation. So this is the order for in order traversal. Okay, so this we can also write the code for that only in these three steps. If you see the code for that, only these three steps are required in the coding form. And what is the difference between pre-order now? Okay, so pre-order, so algorithm is very similar. So same we are applying on this algorithm on any current T node. And after that, the first step here, actually first, according to the pre. So pre means first we will visit the node, visit the current node. Okay, so only we are changing the order of steps, so that the second step will become a first step. Now visit the current node. So that is current node we are visiting. Okay, second step will become a call the same algorithm on left child, pre-order on T left child. And third step is a same recursive algorithm on T right child. Okay, so this is the pre-order algorithm. And post-order, just move this visit steps at the last T. And this first step will be the recursive call post-order on T left. And second step, post-order T right. Okay, and third step is visit current node T. Okay, so this visit is just a, this is not a call or function anything, this is just a print or some basic steps. And these are two recursive calls, these are two recursive, and this one and this one. So these are the algorithms for all in order, pre-order, and post-order. Okay, so for any traversing algorithms. Now how these algorithms are work on the tree. Okay, so now I'll just explain. So how these actually visit the nodes. So A, and I'm writing again, B, C, D, E, F, G. So if we can mark these steps, like I'm just marking this as a left. Okay, left. Just note down this left, print, or R. Okay, so L and R is representing a left recursive call on the left child or recursive call on the right child, and this P is just a print, the current node. Okay, so these three steps you can remember. So what is the order of this? These three are LPR. So we can just write these steps like this LPR. Okay, so steps is always performed top to down manner. So this first step will be performed first. Okay, so this left. When we are calling this left, so that means we are moving to the left child. Okay, and after moving the left child, we are calling the same algorithm. So that means all these three steps will now perform on the left child. So LPR. Now again, the first step will be this. So if you know the that nature of the recursive call, so when we are calling that new function, that new instance of that function will be start execution. So this left, again the same left recursive call, so that if left is available, okay, so that this is the LPR, we will move to the left child. But if there is no so all these algorithms, these steps are written under the condition if left child if left and right child is not there, okay. So in this way we written this steps. So here you can see now there is no left child of this, okay. So this is means empty, so this is first step is now empty, so there is no step because there is no child, so this step will execute without any effect. But now the second step will perform, okay. So print the current node. So what is the current node? D, okay. So for this is D will be print. Now what is the next step is R. So this is a recursive call, but there is no right child, so this will also not affect anything. So only D will be printed at the first step. Now move back. So now recursive call, this all three steps are complete. So we will move back to the previous call, and next step will be execute. So now first step is completed. Next step will move, print. Okay. So print the current node. So what is the node? B. And next step is R. So now R is a recursive call on the right child. So just write all these three steps on the right. So first step is L. So left call, but there is no left child. Print current node E. So this E will print and R. So R is not there, so that will not affect. Okay, so all three completed. Move back. Now all these three completed. So we will revert back to the main call. Now the second step is P. So A will print and our right recursive call. Okay, so right is recursive call same L P R. Now first is left recursive call, left is available, so this one LPR. Now first recursive call this L. Now no left child, print the current node, so F will print and no right. Now move back. Now print step C will print and then right recursive call, so LPR. So left node left, print current node G. Okay, R. So all three steps complete, back. Now all steps complete, back, all steps complete. Okay, so this order we are getting, this is called as a in order traversal. Okay, so how this in order is works, so we get traversing. Now the pre-order, similar to we can perform the pre-order. So B D E F G. Okay, so now pre-order steps are traverse first, or we can write like print and this left, this R. Okay, so now first step is print L and then R. So these are the order of steps. So first step is print current node. So what is the current node? A. So always remember that in the pre-order, always root will print first. Okay, in the order, root will be come as the first position. And post order traversal, that root will come at the last position. But in order traversal, it will come in between. So A, now next call is left. So that left recursive call. So P L R. So first step is P, print B. And the next is left recursive call, P L R, and then print current D. Okay, no left, no right. Then move here R. So R is there. So PLR like this. So print E. Okay. Now no left, no right. Move back. So now right is there. Yeah. So PLR. So P is there. C. Okay. And then no left is there. So PLR. So print current node F. Now no left, no right. Now right is step is there. So move here. PLR. Okay. So print G. So this is the pre-order traversal. Okay, so order is different. You can see root is coming at the first position. Now the post order A, B, C, D, E, F, G. Okay, so steps are here. Left recursive, right recursive, then print. Okay, so L, R, P. Okay, so print steps are coming at the last position. So left recursive call LPR, left recursive LPR. So now left is not there. sorry, I did it wrong. P. Okay, RP. Steps. So left is not there, right is not there. Print. Okay, so D will print first, and then all complete. Now right is there, so L R P. So no left, no right. Print. E will print, and then all complete. So this B will print here. Okay, so all three completed. Now right step. So L R P. So left is there, so LRP, left, no right, print. So F will print, and then right step, so LRP, no left, no right, print G, and all complete. Now print step C. Okay, and now all complete. So this print step A. This is the order of post order. Okay. So you can see root is coming at the last. Okay. So this is identification that sometimes this type of question asks that if order is given, that what will be the binary search tree or something. Okay. So for the binary search tree, it is given here. Suppose if this pre-order is given, okay, so you can start the creation of binary search tree from this side. Okay, in this way, just take this as a root node, and after that insert all node one by one by following the binary search insertion rule. If post order is given, then follow the insertion from this side. Okay, yeah, because you know that A is the root, then take C and insert C according to the binary search, and you can perform all the insertion. But suppose if only in order is given, then it is difficult. It is not possible that we can reconstruct the binary search tree. Okay, by only the in order. But if only pre-order is given or post-order is given, then we can create a binary search tree again. But here, why we cannot create? Because we don't know if only order is given. We don't know what is the root node. Okay, because root is coming in between, so we are not sure that which will be the root node. Okay, so I hope this is clear.
Yes,
Other
sir.
thing is, other possible questions are that is not, I think, in our course, but yeah, for regarding the binary tree. Okay, so I'm just talking about the binary search tree. So we can reconstruct the binary search tree by just giving this pre-order or post-order, but not by the in order. But if we talk about the binary tree only, okay, not the binary search tree, so we need at least two order. Okay, we cannot create a binary tree by just only that one order. So we need at least either this in order and pre-order. Two combination we need actually to create a binary tree. Either or we need in order and post order. Okay, or we need pre-order and post-order. Okay, so these three possibilities there. If you have the combination order in this form, in order, pre-order, in order, post-order, pre-order, and post-order, so you can create, you can reconstruct the binary tree. Okay, but binary search tree can be created by only one order also, pre and post, but not in order. Okay. Okay, so I hope this is clear. This in order, this traversal part. Uh, any query in this?
So we will create the tree using in order, right? Mostly pre-order and post-order are to identify routes.
No, so I'm just talking about if you have a binary search tree order, okay, so that can be reconstructed by only one order, either pre or post, but not the in. But if you have the order for only binary tree, not the binary search tree, okay, so in that case you need at least combination, this either in or pre, or in or post, or pre or post. Okay, so how we can create this in a binary search tree if the right child is equal to that. No, generally we ignore this condition. Okay, so we not insert the duplicate value in the binary search tree. Okay, so if you have the equal weight, to be not add into the binary search tree. Okay, so suppose let me just also quickly tell you how we can reconstruct the binary that, because I have just created binary tree, not the binary search tree here. So let me take in order and pre order. Then how we can reconstruct? Okay, so D B E, A, F, C, G. Okay, this is the in order, and pre-order I am taking with this. So that is just A, B, D, E, C, F, G. Okay, so in that case, how we can reconstruct? So we know that pre-order first node is the root node. Okay, so we can make this as a root node, and after that we will look into the in order where it is exist. Actually it is coming here. Okay, so all the nodes which are coming before this will be come into left side. So D, B, D, B, and E. Okay, and all the nodes which are coming on the right side in the in order, that will come into the right side of the tree. So F, C, G. Okay, but who will become a left child of this A? So that we can decide based on the pre-order. So what is the next node? That is B. Okay, so B will become a left child, and now the D is coming before that, so D will become a left child of this, and that E is coming, because this is a single node, so that we can directly make the child. Okay, otherwise if you have the multiple nodes, just keep that into the left and select, okay, from the pre-order. So E is coming, E is the single node, and E is coming on the right side of B, so that will become a right child. Similarly, now D have already selected, E have already done. Now C. Okay, you can see C is coming first. So C is will become a right child of A. Now F is coming before this, so this will be come on the left side, and this will come on the right side. Okay. Now F and G. So you can see we are reconstructing this by this. Okay. The difference, if in order and post
तो
order is
यहाँ
given.
ना सिर्फ वाईफाई ओपन ओपन रखा करें यहाँ पर हरदम। तो नहीं नहीं वाईफाई
Rizwana.
बंद करने की जरूरत नहीं रहता है, वाईफाई ऑन रखे रहा करें, डाटा भी ऑन रखे रहा करें।
Okay. So, okay, I'm repeating that. So what we are doing, we are just looking the pre-order to select the root node. Okay, because we know that pre-order contains the first element as a root node. So we make this as a root node. After that, we will check into the in-order traversal. Okay, so where A is coming, so all nodes which are coming on the left side will be come into the left subtree. Okay, all nodes which are coming on the right side will come into the right subtree. Then which node will become a left child? We will select based on the pre-order. Then you can see B is coming first, so B will become a left child of A. Then D is coming before that, that will come on the left subtree. E will come on the right subtree. Again, we will select from the pre-order. So that we will repeat the same things. And in the in order and post order, so in order is given like D, B, E, A, F, C, G. Okay. Post order we have calculated like D, E, B. So D, E, B, and then F, G, C, A. F, G, C, A. So this is post order. This time we will only repeat the process, perform the process. And now we will consider post order from right to left. Okay, this side. Now this is a root node in the post order, so this will become a root node, and we will just check from this in this way. Okay, so right to left. Now we will check the position of this each node in order, and we will decide which nodes will come in the left subtree and which node will become in the right subtree. Okay, process is same. So like D, B, E, and this is F, C, G. So now next node is C. So C will become a node. Okay. Now C, you can see, so F is coming before this, so that will come on this side, and this G will come on this side. Okay, so G is now become a node, and F will become a node, and now B. Okay, so B will select from this group. Now D will come here, and this much E. Okay, so E will come here. Okay, so now we reconstruct the tree. And if we talk about the pre and post, A, B, D, E, C, F, G, and post A, B, sorry, D, E, B, F, G, C. So pre and post. So here there is a possibility that you in some case you will not get the same uh, tree. Okay. But what tree will be created by this two combination, that will also generate the same orders. Okay. So that is one possibility here. If any node contains only one child, so in that case this combination will may generate the different tree. So that is the one possibility. Yeah, otherwise if all childs are there, so in that case it will work fine. So here you know that this and this, okay, the both are representing the root node. Okay, here. And after that, every time we will just look that, so we will just calculate the c1 child 1 c2 for each node. Okay, so what node we are just looking, we will just find out the c1 and c2. So c1 is will represent the left child and this will represent the right child. And how we will check this? So for a, okay, so for a, we will just check the pre-order traverse. So what is coming just after this a? Okay, so that will be become a this c1. Okay, so what node? Because we are looking a. So for c1 we will look the pre-order and we will check what is the just right next value, okay, of this a. So that is b. Okay, if same things for c2 we will check the post order. So what is the just previous value, okay, for this a. So that will become a c2 c. In that case, if c1 and c2 both are different, then you can simply make the child. But sometimes there is a chance you will get the same value for that. In that case, you can connect that into either left child or right child. So that is the possibility where there is a chance you will not get the similar structure. But here this is different. So we will make this c1 as a left, so b, and c2 as a right, c. Okay. Now we will look this. So as also you can mark that this is become a node of the in the tree. So b, c, and b, c. So we will not look again this. Now we will check for b. So what are the node possible for b? So b, c1, and c2. So c1, just look in this. Okay. So what is the next node? Okay. So this d, and in uh, this side. Okay. So b, e. Both are different, so connect this. Okay. So d and e. Now we will check for, so also mark this d and e, and in this also, so d and e. Now next we will check for c. Okay, so c, so c1 c2. So in this is the node f. Okay, so f, and this side g. Both are different, connect this f and g. Okay, so then now all are selected. Okay, so you are getting this manifest tree. So these are the possibility for the questions. These type of questions with the combination we have not included in our course, but you will see these courses in the other DSA questions for the tree. Okay, so I hope this is clear. Let's move to the Week-8. Any query in this?
Sir,
Okay. Huh.
could you please explain first one?
This in order and pre-order.
No, the in the last the B and C. How you have taken B and C?
So in the starting, when because we know that what is the root node. Okay, so in the pre-order first node, post order last node, both have the same. Okay, so this will
Yes.
become a root node. After that, for this, for each node which we are looking for. Okay, so what is the left child for that and what is the right child for that? We will check two information. So c1, c2, like child 1, child 2. Okay, and this c1 will represent the left child and c2 will represent the right child, and this c1 we will look into the pre-order. Okay, so
Yes.
c1, what is the next adjacent nodes of a? Okay, this in this side. Okay, left to right side. So this b. Okay, so what node is coming just after a and which is not visited, not in the, become a node in our tree. Okay, so B. And from C, for C2 we will check the post order and which node is coming into the left side of A, just adjacent. Okay, so this is C. So C. And after checking this, if both value are coming different, so directly you can connect that into C1 as a left child and C2 or the C2 value as a right child.
Okay, got it.
Okay, some there is a possibility that sometimes what happen, suppose if in the original tree if only one child is there, B like D. Okay, so in that case you will find here for B you will get a like C1 and C2. So in pre-order you will also get D, and post-order you will also get D. Okay, in this situation. So you cannot confirm that this D is connected either left child or right child when you are creating it, when you are reconstructing. Okay, so in that case you can also create like this B, and maybe you can also connect this. So in this situation you can connect this D either to the left child or to the right child. This is the possibility where the reconstructed tree may be different from the original tree. Okay, for this pre and post combination. Okay, otherwise if both are different, simply connect left and right. Okay, so now move to the week 8 content. So let me open this. So week 8 content basically based on the algorithm design strategy divide and conquer. Okay, so according to the name, we have already used these techniques in previous algorithms, which we have learned in the week 2 and week 3 sorting algorithms. So according to this algorithm, this design strategy name divide and conquer. So means we will break the problems and we will solve each problem separately. Okay, after that we will combine the solution. So this is the way of this divide and conquer strategy. Sometimes, so in some algorithms we actually divide the problem and we solve each part. Okay, so each part of the problem separately, and we actually merge the solution. But sometime we also actually break the problem into half part, and we just ignore the complete one half, and we just solve the one of the half, like searching you have seen in the binary search. Okay, where we just check the middle element and we ignore the half of the part and we search the that uh, only one half of the part. So that is also comes under this divide and conquer, but that is a different version of this, where we give the name for that is divide and decrease. Okay, because in that case we are not solving each part, we are just decreasing the half size, dividing the problem, and we are just using the one of the part of that problem. So that is sometimes gives the name divide and decrease. So that binary search and that type of algorithm that comes under that. Okay, otherwise you have seen this merge sort algorithm where we are sorting the all elements and we are breaking the problem into half and till the one element, and then after that we are sorting. Okay, and then merging. And similar type of quick sort we have also seen. So where we figure out the pivot element position and we break the problem. So what are the elements before the pivot, what are the elements after the pivots, and we call the same quick sort algorithm on the each part, both part. Okay, and so at the same time our elements are also sorted. Okay, so these two are examples, merge sort and quick sort. We have already seen both are the example of divide and conquer. Okay, now in this weeks we are also learning some additional algorithms, so that is also follow that divide and conquer strategy to improve the efficiency. Otherwise the same type of problem can be solved by the naive approach, as professor have explained. What are the complexity by the naive approach, then how we can improve that complexity with the help of this divide and conquer approach. So as we have also improved the merge sort complexity, as you know that. Okay, and log n. So first problem. So there are multiple problems are discussed. So the first, this counting inversion, closest pair of points, integer multiplication, then quick select, fast select, and last topic is just take complexity calculation using recursion tree method. So first thing is counting inversion. Okay. So counting inversion, basically we are just checking the pairs which are not in the order as required. Okay, so how many pairs are there in the given numbers which are not in the correct order? Okay, in correct sorted order. So that we are actually counting here. So that is called as a counting inversion. So let me give the example. So here example you can see already given here. So let me explain this. So this order. Okay, so this lower one, this order is given, and we are just checking this order corresponding to the sorted order. So this is the sorted order. So our order should be this, but our order is given this 2 4 3 1 5. So how many pairs are there which are not in the correct order? So that we are figuring out. So 1 2 3 4 5. This should be the order. So you can see this simple, this you can count like this for 2. So how many elements are there which are coming after that but which are smaller than this?
One.
Okay. So that is only one. So with 2, you can see this is the one pair which is the invert. Okay. And there's no other pair. Okay. So then for same things we can check with 4. So the elements which are coming after that but which are smaller than this. So 4 3. So 3, this is the one pair. 4 1, this is also one. All are fine. Okay. So these are 2. And same for 3. Now how many they are there? Only 3 comma 1 after this. Now 1 is fine, 5 is fine. 5 is fine. Okay. So
Can you
these are the
excuse? Can you just repeat the logic behind what is this reversal?
reversal means so that what order is given. This order is given, but we are just comparing this order with the sorted order. So we are checking that how many elements pairs are there which are not in the correct sorted order. Okay, so that means this sorted order is this one. Okay, so that means if we check about the position, so position 1 2 3 4 5. So any elements which are coming first, and after that any smaller element is coming, so that is creating a invert pair. So that is not in the correct order. So that we are counting here.
Okay, the order
Okay.
mismatch. Okay.
Order mismatch. So this 2 and 1, this order should be 1 and 2. This should be the sorted order, but this is the incorrect order, incorrect pair actually. We are looking only the pair which are not in the correct order.
All right.
So each pair we are figuring.
How is it related to the number of crossings?
So that things, this is just a way to represent that. So we are just mapping to the sorted order, and we are just mapping to the same value. Okay, so after that, what are the cross points? That is also representing the same number of pairs which are not in the correct order. Same in total number of inversion pair. But the information is same. But this is just a representation.
True, but here at least the top line is sorted.
Top line is sorted, and this is the actual input order what we have.
Is this looking like a puzzle that you have put it in GR2, GPR2?
In Week-8,
Yeah, for week 8.
I think that is the same question, not to puzzle like this. So that is the same inversion pair question.
What?
Okay, so this is just like a representation. We have already seen this. These are the pairs which are not in the correct orders. Okay, so the 2 1 4 3 4 1 and 3 1, and that is called as a inversion pair. So that we can also count like this diagram graphically. Okay, so how many cross point we are getting in these lines. So that is also represent the same information. Some examples our professor have given where this algorithm can be used. So that example is like a ranking. Okay, so like you have these multiple OTT platforms where you what movies you are just watching, what type of movies you are watching. So that actually internally identify your interest. Okay, and after getting your interests, they match your interest with the another similar type of interest that they have. So like this is, suppose this is your ranking and similar type of any another user ranking. Okay, so that we figure out that how many inversion pair between two different ranking order. Okay, so what is the, if any order contains the minimum number of inversion pair means that have the very similar ranking. Okay, suppose if two users are liking and giving the ranking for some movies or something, so that you are giving sorry, one second. Suppose 1 2 3 4 5. Okay, this is the user one ranking. Okay, and user two ranking is also similar. Okay, 1 2 3 4 5. You can see if you compare both order and you figure out that what is the inversion pair count for these two. Okay, so for user one correspond to user two ranking. Okay, so here you will get a inversion count is 0. So that means if inversion count is less, so that means ranking is very similar. Okay, if inversion count is more, so that is representing the that interest is not matching actually, or ranking is not very similar. So based on that, so they checks your interest, what you are watching, and they checks with the other users ranking. So what other users are liking. So other users are watching the same things, and based on that information, what they are actually watching the other things. So sometime OTT actually suggests that things to you, means you may also like the that things. Okay, that movies or that series or something. So that type of, this type of algorithm used in these suggestions. Okay, so what you may like. Okay, if you are watching something, if you are watching action movie, so that identify your interest and match with the other user interest and figure out that what may your more interest to the others movie. Okay, so this algorithms maybe this algorithm basically used of this type of information to finding out the similarity. Okay, so in this is the one problem, and how we can find out this inversion pair count efficiently. So here we can use the same merge sort algorithm, same merge sort algorithm concept, and we can figure out the number of count, inversion count here. Okay, so how we can use that. Okay, you can see the algorithms are given, but how it is counting. Okay, so let me explain you. Because you know that the work of the merge sort is basically merge the two sorted array. Okay, so that you know that one merge function is there in the merge sort algorithm that takes two sorted input, sorted array or sorted list, and that merge two sorted list into a one sorted list. Okay, so same algorithm we are using here, but at the same time, so we count the inversion actually. So how that algorithms, I am just giving the idea of that part. Suppose you have this like one. Okay. Suppose 1 5 8 10. This is the one input list. Okay, for the merge operation, and another is like 2 and 4 6 7. This one. This one. Okay. So this is the two list we are getting, because this is a left list and this is the right list. So this, during the merging of these two lists into a one sorted list, we will get how many inversion pair in this. Okay, So that means we can write like this: 1, 5, 8, 10, and 2, 4, 6, 7. So if this is the order, and we are merging these two part, okay, and during the merging we will count this. So how we can count this? So in the merging operation, we takes the variable for one list and another variable for second list, and we create a one final merge list. Okay, so let's see. So when we are creating this one left, okay, so this is the left part and this is right array, left array or right array. So if we are checking I value, what is the current I is 1. Okay, if this 1 is less than 2, this j value. Okay, so this will be moved to the C according to the merge operation. So if we are getting this I value is less than j value, so that is fine. Okay, so because that is coming in the correct order. This is smaller, this is bigger value. So that is fine. So we can directly conclude that we will not consider this comparison as a inversion count. So this is fine. So because 1 will move to here. Okay. Now I pointer will move to the next element. Now in this case, when we are comparing 5 and 2, now you can see the left array 5 element is greater than this 2. Okay, so this is a inversion pair. And once we are finding out that this 2 is creating a one inversion pair with this 5, all the remaining elements which are coming after this will also create a inversion pair with this 2, because this is sorted order. Okay, if after each element after this 5 will be the greater than this. If 5 is creating a one inversion pair with this 2, the remaining element will also create a inversion pair with this 2. So when we are comparing this 2 with 5, we will directly check what is the length of this. Okay, length of this is 4 element, and currently we are at the second element. Okay, so we will directly check how many elements are there. Okay, so if this is creating an inversion pair, so we will directly check 4 minus 2 plus 1, total 3 elements. Okay, so 3 elements are making the inversion pair with this 2, and we will take one some counter, so that inversion pair, so ip, and we will directly add this information 3 into this. So 0 plus 3, 3. Okay, so that means with this 2, all these 3 are creating a inversion pair. Okay, so now next step, this 2 will move to the here. So now j will become here. Now when we are comparing 5 and 4, again you can see this is greater, left array value is greater than to the right array value, current value. So same things, if this 4 for 5 and 4 is creating inversion pair, all the remaining value will also create a inversion pair with this 4. So same information, again we will add 3 here with this, for this 4. Okay, and then so we will move to this 4. Now j becomes 6, and now you can see the 6, 5 are in the correct order. So 5 is coming in the left side, and 6 is coming in the right array. So that is in the correct order. So it will not increment the inversion count. So 5 will shift here. Now your I will move to the 8, again 6 and 8. So same inversion pair is creating. So any element is remaining will also create the inversion pair with this 6. So 2, you can see 2 elements will directly add here this information. Okay, so now 6 will move, then j 7. So 7 is also creating with this 8. Then remaining element will also generate an inversion pair with this. So again 2. Okay, so this 7, and then remaining elements are only there. So 8 and 10. So this is the merging process, and during the merging process, we are also counting this information. So total 3, 3, 6 plus 4, 10. 10 inversion pairs are creating in this.
Does this mean there will be 10 intersections between these two lines?
Yeah. So if you so if you compare with this 1, 2, 4, 5, 6, 7, 8, 10, and this order is 1, 5, 8, 10, 2, 4, 6, 7, then if you will create a line in to match each, so that will create a 10 intersection.
I see.
Okay, so that will represent the same for this. So we are using this merge sort of operation. Now in this merge sort of operation, that we are counting this information. So you can see this count variable we are taking. So now you know that how this approach is counting this inversion pair. You can write your code also for merge if this code is not very easy to understand, but uh, you can see the code is doing the same thing. This is taking two array A and B here. Okay, so A and B here, and after that we are doing the merging process by this. And we are checking the same things if I is become M. So that is meaning that one array is completed. So C dot append BJ. So this is coming under the while loop. Yeah. So if any array is completed, so another array elements we will directly append into the final array. Okay. So this I, this is for the same condition. LF is also for the same. But here you can see this part. If AI element is less than BJ elements, then we are simply appending the AI element into the final list, and we are moving our counter I and K. We are not adding any information for the inversion count. But the reverse condition, else part, okay, when BJ is smaller than AI, that is making the inversion pair. In that case, we are adding our counter to y m minus I. Directly, we are appending this information. Okay, at any point we are getting this AI is greater than BJ. In that case, we are directly adding M minus the current index of the I. M is the length of, okay, M is the length of A. So how many elements are remaining after that point, that will directly add.
If A and B are interchanged, will the result be the same?
A and B, sorry.
If A and B are interchanged, we've taken a left and right merger, right?
Huh.
If the same numbers, if it was order was changed, will the number of intersections change?
It will definitely change.
Why? The number of reversal going to be the same, right?
No, so if you are talking about like what
The
we
example
have taken,
yeah, 1, 2, 3.
so like 1, 5, 8, 10, and like 2, 4, 6, 7, like this. You are saying that if we are taking this as a and this as a B.
Correct.
So definitely this is become like 2, 4, 6, 7, and 1, 5, 8, 10. Okay, this is become a and this become a B.
Correct, but will
So now we will come.
the result
will change definitely. Yeah, will change.
Why?
Because this order is completely changed, na? This order is completely changed. So now if you see this 1 and 2, this is okay. So we have to
I don't think
change the change. No, it will change actually. So let me 1 and 5, 8 and 10. Then perform the same thing again.
Yeah,
Okay?
let's see.
So you can see 1, this is B. So this time 2 and 1. This 1 is creating the inversion with this directly.
Let's go to the numbers. 3. It's order 3, right? 3, 1 is ahead of 1 and 2.
No, this is left array. This is now right array.
Fine.
If this, 1 is creating inversion with this 2 directly. Okay.
Number
So all 4 will be added directly because
4,
this is creating 4 count.
Fine, 4.
Okay. Now this 1 will be added here. Now with 2, this is fine. Okay. So 2 and 5 is fine. So 2 will insert here. Now just compare with this 4 and 5. So 4 will move.
Again,
Now here.
2.
This is the inversion. Okay, so 5 and 6, 2. Yeah, plus 2. Okay, and then 5 will move here. So then 8. So 8 and 6, 6 is fine. 7, you can see 7. Total become only 6. So or that count is changed.
B in the left side now, what happens?
What is the in the left side?
No, what you have written originally. B and A. Suppose 158 is in the left and then
that was 10. No? We are getting 10 for that. Why? No, I think this is changed.
Numbers are changed. I think it should also be 6. I just want a confirmation.
Okay, just check again. Okay, so just check for this part then. So 1 and 2 is fine. So 1 I'm getting. Then 1 and okay, so 5 and 2. Okay, so this is creating inversion.
Yeah, 3.
So 3 plus, and now 2 will come here, and then 4 and 5. So again, it is creating inversion.
Yeah.
So plus 3.
Okay.
Okay, and then 6. Yeah, 4 is come here, and then 6 and 5. So 6 and 5 will come, 6 and 8. Then it is creating inversion pair, so plus 2. Okay, 6 with 8. Correct?
I'm not. Yeah, I see the numbers, the logic, but it doesn't make sense because how? Why should this change?
Actually, you can see our order are changed. If we are taking this as a and B, but we are always comparing with this sorted order finally. So definitely, if our order is changed, so count is also changed with the same sorted order. So 1, 2, 4, 5, 6, 7, 8, 10. So we are comparing this order with this same order. Okay, and other order is 1, 5, 8, 10, and 2, 4, 6, 7. So this is the different order totally. So this will create another different count with with the same corresponding sorted order.
Okay, thank you.
Okay, so yeah, this is the logic for this. So as you know that merge sort takes order of n log in time. So we are nothing doing additionally here, only just taking this step, count plus equal to m minus I. So that will not impact the complexity, and then that information we are directly getting into the return value. So that things we are finally counting what is the count value for the left call, and what is the count value for the right, and what is the count value for merge. All this value we are getting from the each call, and then we are adding all this information, and we will get the total number of inversion. Okay, in the complete process. So that complexity will remain n log n for this inversion. So this is the first topic, that inversion pair count. Next topic is that closest pair of points. So this is related to the 2D 2D like scenario, 2D graph. So we have the axis x. So we have the x-axis, we have the y-axis. Some points are there, not like this. Like x-axis and y-axis. So we have some points on this plane in two-dimensional, but here some conditions are there. So for this problem, conditions are there. No actually points come into the same line. Okay, same line or same column. That condition is given. Otherwise, each points have two coordinate, like what is the x coordinate and what is the y coordinate. So then we are figuring out that what is the pair of points which have the closest distance in all these points. So if you think about the naive approach, you have to compare each point with you have to calculate the distance between each point. Like this is the P1, this is P2, this is P3. Okay, so you have to calculate the distance between each P1 to all points. So that will become a n square type of work. Okay, so where if you have n point, so n square operation you have to perform to calculate the distance between each pair. Okay, but how we can do in the better way, so that is discussed in this algorithm by the divide and conquer approach. So here the approach is we actually break this plane into two parts. Okay, so let me show you. This algorithm is given. Let me open the slide for this. Okay, so one second. To this pair of points. So you know that this is the distance formula is given between 2 points, so that we will use for the calculation distance. But after that, now finding the closest one dimension is fine. Let me check two dimension. Yeah, two dimension. Yeah. So here the steps, we are just breaking this given n points we have. And first step, these are the steps actually we will perform. We will just sort all the points by the x coordinate. Okay. So we have the each coordinate with two value, x and y coordinate. So first step, we will just sort all the points by the x coordinate that will comes under the px category. Okay, and that sorted order of the points. Py is the this is a set of points in the order. So this py is representing sorted the points by the y coordinate. So we are collecting this, and based on this information we are dividing that. Okay, so after sorting we have this px and py, and we are dividing this region, complete this p region, into two parts, q and r. Okay, one vertical line in this region. And next step, so how we are computing this qx and qy. So now that what we are doing actually, we are dividing the problem. So we are dividing our problem into different sub part. Okay, so that we are dividing the problem into one q category, q region. So that one region we are calculating this q, and another region we are calculating this r. There is also another region that is actually a border region. So because there is a chance that any point may contain the closest point that is coming in the that in the cross lines. Okay, so suppose this point and this point, that may also contain the minimum distance in between. So because of that, generally these three regions are there basically. Okay, we are calculating by these two regions, but we will also check for this borderline. Okay, during the calculation, and this region will be different. That distance between points will be calculated separately. So this q, what are the points coming in this q region will check separately, and this r region will check separately. Okay, so that same problem we will divide further again. So like this q region again we will divide further till the 3 points actually. Okay, so 3 points distance we can easily measure. So if you see the implementation of this, okay, so in this is not coming algorithm. Let me show you the code then. Yeah. Okay, 1 second. Distance recursive. So what point we will divide these problems? If only 2 or 3 points are left, okay, then we will break this problem into the sub problem. So like merge sort, we are breaking the problem till the one element. Same things, we are breaking the problem into a sub problems till the if any region contains either 2 point or 3 points. And if we are getting 2 points and 3 points, we can directly calculate the distance by this formula. Okay, so this formula, you can see this condition. Okay, and similarly as for 3, so that is also a one step operation. So you can see we are just checking the minimum distance between these 3 points. So this we are making as a base case, because we are writing a recursive code for this. So this we are making as a base case to stop the process. Otherwise, if we have more than 3 points, so then we are performing our task. So more than 3 points, divide the points by points around median of x coordinate. So we will take some that median value. So that what is the that 1 second. Total number of s, how many that points are there in the px region. 1 second. Okay, X Q Y Y. Points. Yeah. So this is the basic approach. So as we said that px and py value how we have calculated. Px was the list of sorted element points based on x coordinate. Py was the sorted points based on the y coordinate, and we are dividing this region into qx and qy.
How do you choose the division P?
That is a median point actually. So like we are just checking the x coordinate and we are just checking the middle value. So we have the sorted points based on the x coordinate, correct? So px value you can see.
Does it ensure on both sides we have the equal number of points?
No, that not ensure that.
I'm sorry?
No, so you can see px contain the sorted points order based on the x coordinate,
Correct.
and we are checking the middle point.
Middle or median?
Median. So that median is the same things. In the sorted order, median will come in between.
Not necessarily. If it is skewed on the one side, then what happens? If there are more number of points on clusters, dense, the other side is very sparse.
Okay, so suppose what you are saying that if suppose if this side points are
If there is a cluster on the right side and then there is a very few points on the left side. So still I take it the midpoint, or is it a median? Means then yeah, median is
median. This is a median actually.
basically I'm ensuring equal number of points from both sides.
So that is not the guaranteed actually. Equal is not the guaranteed.
Median is supposed to be like that.
So median is like if you just so what you are doing actually you are sorting all these points based on the x coordinate. So this coordinate, this side. Okay.
Median means it's equal side. I mean, it's both sides are equal.
That's actually suppose if you have 1, 2, 3, 4, 5, 6, 7, definitely you will choose this as a median, no?
This is distributed equally. If I take 1, 2, and 9, 10, 11, you know.
Still, so 1, 2, 9, what you said, 9, 11?
Yeah, 10, whatever it is.
9, 10, 11. Still, then it will come as a median, no?
Yeah, it
So
will
you
be.
will get a on this.
Okay, both are right. It will be equal number of points on both sides.
Both sides. Okay, median is the middle element in the sorted order, correct? So you will get a equal distribution based on this. So we are just marking this as a borderline, and we are just checking this as a Q region, this as a R region. The same things we will do inside this. So same things we will repeat the Q. So as how we consider this is a PX and PQ. Same things we will do in the Q region, this Q region and the R region. So we will make as a list as a QX and QY, and we will also make as a RX and RY, same list. And we will again divide it in the same way. So this is the division process. Okay. And recursively, we will compute the closest pair this algorithms on this Q, this region, and this closest pair on this RX, RY region, this region. So, and we will reach to the base case, and base case when we will have only 2 or 3 points, we will directly return the value of the distance. So these are the two steps. We are just finding out the what is the smallest distance between in this region. So this is the just largest picture area, but that problem will be start solving from the 2 or 3 points after breaking. So in that case, so that means this part we are just checking all element, what is the distance in between all elements. Okay, and same things we are doing this part. And suppose this dq, we are just checking that in this q region, dq value is the smallest distance value, and the same region dr. So dr we are considering this as a dr value is the smallest distance between any two pair of points in this r region. So this is the two value, And we will also figure out that what are the, so we will just figure out some border area with this line, and that border range will be decided based on this dq and dr value, which one is the smaller. Okay, suppose dr is the smaller, so that border we will take only. So what is the dr, this distance? Okay, so between this border, so dr by 2 this side and dr by 2 this side, and we will consider the points only in this region on the border, because that can contains the less distance between compared to this dr. So we will just find out the distance between the border, these elements. So what is the distance between this cross all these, and suppose we are getting some d something new value like db, and then we will check what is the smallest value in all these three. That will be the solution for this. So this is the overall idea.
What are the benefit of this specific algorithm?
So this improves the complexity actually. This improves the complexity. So in naive approach, when you are calculating the distance between each point to every other n-1 points, so in that case you will get a order of n square complexity. But by this approach, you will get a n log n solution, because you are dividing the problem into a subproblem, and each problem is solving separately. So now in the q region, these points are not comparing with this r region points. This calculation is not happening now. Okay, so this part is only we are just checking separately, and this part we are checking separately. So we are just reducing the distance calculation between the points. So this is just become a divide and conquer approach, and each problem solved separately, and we achieve the n log n complexity for this. So if you see the code now, so this is the idea of this. Okay, and let me open that. So each algorithm we are learning here to just the efficient as a efficient algorithm. So you can see S is the length of px point. So px here px is the list. We can consider that this is a list of points based sorted list. Okay, based on the x region. This is the S actually the length of that, and we are just selecting the middle point as a median of that. Okay, and then we are creating the region qx. We are taking the half element. Okay, so that only till m point, and rx the remaining right side element, and xr this is the minimum, that is the point value which we are taking rx. So yeah, so what is the first element value? That will become a that xr value. So this is just a median point value. So what point is actually coming at that borderline, vertical borderline? So that we are taking as a xr value. And so we are creating again, we are constructing this qy and ry separately, these points. So we will collect all the points which are coming in qy region and ry region, and the same things you can see. We will call the same function again in some point. That yeah, same you can see. So delta, you can see this part. Delta is the minimum distance between qy region we are getting and ry region, that rx ry region. Okay, so we have again break the point px and py based similar to this at the first step in the qx region and that ry region in the same form, and we pass the same region again into the same recursive call. So that will return a minimum distance either from left or right region. Okay, so that is the recursive call in this part. So recursive call will do the same process again. It will break the again, and then we'll check the same length again. If that is the greater than 3, then it will do the same thing again. Otherwise it will directly return the value from this base case. Okay, after getting this delta value from minimum value from left region and right region, Then the next step is figuring out the point which are actually coming into the border line. So that we are checking. So because we know that XR was the point, that is the vertical line point, and we will check what are the points are coming on the delta distance. Okay, so total distance is delta, which is selected as a minimum distance in the left or right region. So that area we will make. So what are the points which are coming in this range? Okay, from this XR point, left or right, and from that points, then we will. So the next step is in this line actually. So you can understand this DQ is selected as a sorted distance from this region and this region. After that, we make this border. Okay, based on suppose this, what is the delta? This delta is actually a smallest distance between DQ and DR. So that we make the border, the region, and in this region we will again check what is the distance. So in this border region, we are making this. So we are taking this delta on the left side also or right side also. So because any point can come here and here like this, any point come, any area it may become. So we are making this smaller distance on this side also, this side also. And in this region, what we will do, we will sort the points into based on this y-axis. Okay, so we will sort the points on this y-axis, and then we will just figuring out the okay. So here how we can make this as a that linear operation. So that is also important here. So suppose if any point is coming at this point in this vertical region, this point, and another point is coming this point. So that should be checked or not. So that is actually will not be checked because this square region you can see, this is also indicating this some distance. So delta y2, delta y this 2. Okay. So if we figuring out this total 16 region, so what points are coming in this region, we can only restrict to check on this region. Any point is coming outside of this region, definitely that will contain the distance of this delta. This okay. So that is no need to check. So we will just make some container like this area, and we will check the points which are coming in this region. That will only be checked for the distance, because that may generate a smaller distance. So that is also 16 we are taking. That is also maybe reduced more. It is also mentioned in the book. So that is just for the safer side. So we are just making this as 15. Any point is coming in this, so that should be check only the remaining 15 region. Okay. So that means every point, how many points are coming in this region, we will check only the next 15 point after sorting. So any point is coming. So after sorting in this axis, we will check that point distance with the next 15 points only. So that 15 points may come in this 50 region. So if any point is coming here, so next 15. So that may, as I said, that may be reduced also, because we are checking to the upper side, not the lower side. But that make as a linear actually. Suppose if n points are there, so that will check only 15. So it will become a 15n operation. Okay, so that complexity will become order of n. So that is the next thing. So that is discussed in the example. So that part we are doing here in this code. So after arranging the points based on this SY, okay, so we have collected all the points in SY axis. Then in this SY axis, you can see we are running size of S. Okay, len of SY. ABS point XY. Okay. So you can see this loop. So we are running this point for the each point in this this SY. but we are checking only for I plus this 15. So what is the current point I? We will check only till I plus 15, next I 15 points. So this loop will become a only 15 constant value, and this will become a n. So total complexity of this part will become a 15n, order of n. Okay. So that will not actually, so if suppose if both loops are running n times, so again same thing, complexity will become a order of n square. So that is the case if all points are coming on this region till the border point. Okay. So in that case, this will work like as a order of n square, but we are only checking with the next 15 point. So in that case, that will become a order of n operation, this part. So now complexity is similar. So we are breaking the problem. So one problem we are breaking like in two problems, sub problem. Okay, so that means we have the n and n by 2 and n by 2. So this is the breaking steps, so that we will divide further n by 2 like this, n by 2 and n by 2 and again further. But each steps, okay, so when we are breaking that, we are also performing this border part, so that is taking order of n time. So order of n time. So that is the additional work after breaking that problem. So that will make the same complexity as merge sort. So each steps, if we have the n, so total of number of that n step is required for this middle part. If this n by 2, so the n by 2 and n by 2 plus, it will also make as a or n step at the each level. Okay, so n steps. So the total number of levels will be log n, and each steps we have the n steps. So it will become a n log n steps. Okay, so this problem you can take some small example, so and you can figure out the you can just apply the dry run on this. You will also get the clear idea that how this algorithm is working. Overall idea I have given to you how this is breaking the problem. Okay, so you can take some points like this and manually, and you can just go through once. Then you will understand that how this algorithm is working at each steps. Okay, so any query in this closest pair of points? Okay. The next problem is this integer multiplication. So this is again the same type of problem. If we are multiplying two numbers of n that digits, so that is will take the naive approach will take generally out of n square time. So that one this algorithm we have this Karasuba algorithms. So that actually improves the complexity to this order of n log. That is the different, I think, 3 by 2 something. So teacher multiple. So complexity improves to this is the recurrence relation for this. So 3t n by 2 plus n. And we will solve this. So we will get this complexity. This this n to the power 1.59. So that is log 3 actually, and log 3 we will calculate as a 1.59. So that is improved okay, compared to the n square. So that is the similar things. We again use the divide and conquer approach in this, and this problems is divided into sub problems. So like you see the code. So what these are the steps actually. Okay, so we are calling this fast multiply x and y are the two value, and both have the same number of digits n. After that, this is the base case we are making. If n equal to 1, we will directly multiply. One digit, we will directly multiply. Otherwise we will just break the digit. Okay, so we will just break the digit. Like you can see this 3 4 is given here, 3 4 and 8 9. So this is the 1 and 4 digit we are getting this in the main call. But next part, this will be break into two different part. Okay, so XHXL. So that will get like 34 and this is 56. Okay, this calculation. And this value again, this will calculate as a 89 and this 02. So if you will calculate this, because we are performing this multiplication on decimal number, so because of that we are using this 10. If you are working with the binary number, so you can just put 2 here. Okay, so just perform this operation x floor division, this 10 to the power m. So that will generate the same information, that will break the number actually. Okay, so by this calculation, so 34 56, if you divide this by floor division 10 to the power 4. Okay, so 10 floor division 10 and to the power m is okay 2. Okay, 100. So if you will break this, so you will get a floor division part only. Okay, so that is just like this 34. Okay, 34. And same time, if you will divide this, so you will get only the remainder part. This is percentile. Okay, remainder operation. If you will divide this, so you will get a remainder only 56. So we are breaking the problem, and again we are calculating some additional information. We are just adding this XH and XL and this formula, and after that we are calling the same function again with this different data. So you can see we are calling the fast multiply and XH, this XH, YH and M value. So M is now become 2. So same type of information P, Q we are just calling, and R. These 3 times we are calling the same function recursive, okay, with the smaller data. So we are breaking the problem and we are just calling the same algorithm on that sub problems. After that, what we are getting, we are just calculating by this formula and we will get the result. So in this way, you can see all steps.
I have one question.
Yes.
These mathematical jugglery, are we supposed to know during OP?
Actually, no, not for the OPP. Yeah, these algorithms are some standard algorithms, so that is generated for some improvement. But this type of calculation is not required for the
I
OPP.
presume this is more for information purpose. Such algorithms exist. They are not going to test me for.
No, not. We will generally disclose just pair of points. We generally not gives this in detail in the exam.
Okay, thank you.
Okay. So here you can see 3 times we are calling this, so that become a like t n 3 t n by 2. Okay, and the remaining part is simple plus 1. Okay, constant, all other constant operation apart from this. And then we will calculate this, and then we will get the complexity. Not one actually. I think we have the this t n operation. Okay. Okay, this is not the. Okay, so and we are not getting from this part, but yeah, this part actually we are getting some information, because here we are performing some multiplication and this information. So because of that n value we are getting from this part. So then this become with this recurrence, and then we can solve this and we will get the complexity. So how we calculate the complexity by this type of recurrence, that is the last topic of this week, recurrence tree. So I'll explain that. Okay. So this is one algorithms for divide and conquer approach. So the next is quick select. So quick select, yeah. So quick select is, this algorithm is basically used to find out the third smallest or third largest, this type of information. So here actually we are searching something. We are not performing any particular any process. We are searching any element. So that search element means this is comes under divide and decrease. Okay, that type of category where we will remove the half of the part. Okay, so the same algorithms like quick sort, as you know, that pivot element. Okay, so that approach we used to find out the kth smallest value in this order. Suppose if any random order is given, uh, like 2, 4, 5, 1, 3, 6, 8, 9, like this. So we are figuring out that what is the second smallest element in this. Okay, second or third smallest element in this order, random order. This is not a sorted order. So how we can figure out this? So one step is just sort the order and then figure out. So that is by default n log n complexity is there. So if we use the merge sort, but how we can improve more with the help of quick select. This quick select is just use the approach of quick sort. Okay, so after partition process, suppose if we are taking this element as a pivot element, so pivot element, and after partition process, so that we will get a correct position for this. So this 2 will come at the correct position where it should come in the sorted order. But before that, all elements will be the smaller element, or before after that all element will be the greater elements. But the position of this is indicating that this is coming at the correct position. Suppose it is coming at the second position, so that means this is the second smallest element. Okay, so what pivot element is coming at any particular position, so that is representing that position smallest element. Okay, so second smallest, this is representing a second smallest element. Suppose if this is for the second, and suppose if we are taking 4 here and 2 here, so we will get a 4, that position, this 4 element, 3 element will come this side, and the remaining element will come this side. Okay, so we can say that this is a fourth smallest element. And suppose if we are looking the second smallest in this example, uh, so for the first pivot we are getting the information, this is the fourth smallest element. So definitely second smallest will come on this part. Okay, not this side. So we can completely discard this part. Okay, we can completely discard this part. We will not check this side. Only we will call our quick sort algorithm, or this quick select algorithm on this left part, because we got the fourth position element. Second position element will come only this side. So we are just discarding the half of the part. Okay, so then we will do the same process. We will pick the pivot element and we will check, and we will decide based on the that pivot position, and we will again decide which part we need to check. So you know that the same information we are using, which we have already used in the quick sort algorithm, pivot position for finding the kth smallest element. But the problem is, we have already seen for the quick sort algorithm, the worst case is order of n square. So what is the possibility that if our order is in descending order or ascending order? Okay, if we are selecting first element as a pivot element, and if our order is either sorted or reverse order, sorted in reverse order. So in that case, we will get the complexity order of n square, because our pivot element will always come at the corner, and we will always perform our quick sort algorithm on the remaining n minus 1 element. So that will become like a selection sort, all this type of algorithm, and order of n square algorithm. So this idea we are using inside the quick select algorithm. Okay, so same type of in quick select algorithm. So that worst case complexity is still order of n square. But how we can improve this? So that we can improve with the help of finding a median element in order of n time. So if we can figure out that what is the correct pivot element. Okay, so that is the one algorithm we have, median of medians algorithm. Okay, so that actually figure out the correct pivot element, and that pivot element definitely will not come at the any corner side. So that actually remove the worst case situation for this quick sort or quick select. Okay, so how we can what how this algorithm is actually works. So in this algorithms we divide our complete list into a block of 5. So as representation, you can see, so what we are doing, we are dividing our complete elements into block of 5. Okay, and we are sorting our elements each part. Okay, so this is the first 5 element we have that breaked. So we are just blocking all these five elements, and each part we will sort. Each part we will sort, and we will check the median element. What is the median element in the each part, 5 blocks? So that means this become a fixed length actually, 5. So if we will sort this will become a 5 block 5. So that is actually constant time. Okay, this is not depends on the input order, and this become a constant task 5. Okay, so we will just perform this with the each block, and after getting all the medians of the each block, again we will do the same thing. Again we will break into the five blocks, and we will do the same thing. And in this way we will just perform we will find out the median elements. So in this idea, you can either take you can see this diagram. So after doing this process, suppose we are selecting this as a middle element, this point as a middle element, definitely this part will be the smaller. Okay, because all elements which are coming in this part will be the smaller elements. All elements are coming on this side, actually the bigger element. So this is the part actually, this the length of this 3 into length of L by 7. This is the part actually. Okay, and similar thing, this part will be the greater than. So that is the another side. So your pivot element will always come in this region, 3L by 10 and 7L by 10. So it will not come either in any corner. So that will actually prevent to come into the worst case. Okay, so we are selecting this element as a median element, and that will come in between this range, not at any corner side. So in this way, it will improve our worst case situation for the quick sort or quick select, and then we can improve our complexity to n log n. Okay, because we are selecting a good pivot element. So the selection of median elements should be performed in order of n time. Otherwise, then we will not get the benefits of this. So this is the code for this. You can see how we are doing this. MOM, we are getting the list, and so you can see this. And if length of L is less than 5, we will directly sort this and we will return the answer. Okay, if it is greater than this, we will create a median list, one medians list, and for each 5 blocks. Okay, for each 0 to 5 blocks, that means five steps actually we are going. So I to I plus 5, we are just creating a new list, and we are sorting then, and we are appending the middle element after sorting into the M list. Okay, and then we are returning medians of median. Okay, so then we will repeat this process. So again calling this MOM algorithm on this median. So same things process will be performed on the medians elements. So in this implementation, you can see what complexity is there. So we are running this loop. Okay, so this is the only linear type of loops, and each times we are just so sort function, this is only generating 5 log p type of complexity. So n into 5 log p this constant time, or total complexity will become order of n only. Okay, so that means we are selecting a one good pivot that will not come into any corner side, that will always come in between. uh in Okay, and that it will actually remove our worst case situation for the quick sort. So same pivot element things we can also use with the quick sort algorithms, and then we can improve our worst case situation for the quick sort. And same this MOM algorithm we are using with the quick select, so that will also improve. So quick select algorithm. This now we are just giving the name as a fast select using MOM. So you can see this is the MOM part, and we are selecting our pivot element with the help of this MOM, and then we are doing the same process what we are doing in the quick select. So it will improve the complexity and the that what will be the recurrence relation for this uh, Tn equal to Tn by 2 plus n. Okay, because this time is for selecting the pivot element, and after selecting the good pivot element will come into the between, and we will reduce the remove some part, that half part. Okay, so because of that we are taking this Tn by 2. Otherwise the previous case, the that for quick select, that the same type of situation was there. So Tn was Tn by -1. Okay, plus order of n. Okay, so that was the recurrence relation for worst case of quick select, but now that is improved to this one, and it will actually generate the complexity of order of n.
Sir,
Huh.
sir, shouldn't it be twice of Tn by 2?
No, for selecting, we are not checking the part. Actually, if we are coming at any particular region point, okay. Suppose if our pi, we are just selecting the seventh smallest, okay, seventh smallest, and our list contain like 4, 3, 1, 1, 2, 8, like this. So this 4 will after we will select this pivot. Okay, pivot we are selecting using this MOM, but if this suppose this MOM selecting this 4 as a pivot, and 4 will come at the fourth position. Okay, so all small element will come this side, greater element will this side. So this is coming at the correct position, and it is also indicating that this is a fourth smallest. So no need to check this left part, because we are looking for seventh smallest. So seventh smallest will definitely come on this right side. So
Yes, sir.
we
Yes.
are okay, we will only call our quick select or fast select on this right part. So that means we are only calling one time that algorithm on the half part. So
Understood, sir.
because of that, this will become Tn by 2. Okay, so this is, and same things quick for quick sort, that worst case situation will improve by this, and complexity will become order of n log n. And yeah, so this is the fast select. Okay, so that is the last topic. So recursion tree. So we have already seen multiple recurrence relation for each algorithm, because divide and conquer generally use the recursive approach. Okay, and recursive approach, to calculate the complexity for recursive approach, we use this recurrence relation, and to solve this recurrence relation, we can use this recursion tree. So that actually this is like is similar to tree, and tree indicate the call structure. So we just start with like t, and so first call. So t and we start. So suppose if we have write like t n equal to 2 t n by 2 n plus n. So suppose this is a recurrence relation for any divide and conquer approach. So t n we start with this as a root node, and then how many calls we are doing calling from this. Okay, so we are calling two times. So that t n by 2, and this, that means we are calling the same problem on two sub problem. Okay, so now we are breaking this. So t n by 2, and apart from this is also taking some additional time, so that will consider as a, like additional time. So when we are just combining the solution, so we are getting this order of n time. Okay, order of n, or n you can write like this. So at each steps we will do this. So if we have the n elements, we are taking this n steps to merging the solution or combining the solution like this, or any additional steps. And now this is the sub problem. Here the input is n by 2. So additionally it will take n by 2 steps. Similarly, here the input is n by 2. It will additionally take n by 2 steps. So at this level, n by 2 plus n by 2, it will also become n steps. Now again, again this problem will break into same Tn by 4. Okay, Tn by 4, and similar this will break Tn by 4 and Tn by 4. So this is the again recursive call. And each time, so T, if we are calling Tn by 4, so this is the additional steps plus n by 4 at this step, plus n by 4, plus n by 4,
Sir,
plus n
I'm
by
not
4.
getting why n is reducing. Additional step means?
So like if you remember the merge sort algorithm, okay, so in merge sort algorithms, what we are doing, we are breaking the problem into two parts, left part and right part. But after that, we are combining the solution, combining two list into a one list. So that actually takes the that additional things, additional steps. So if you see the algorithm, that merge sort algorithm, so uh, complexity base,
Yes, sir. To merge, we take n, order of n time.
order of n. Na? So
Yes,
if you
sir.
remember this steps, when let me show you again.
Uh, So I understood like
Ha,
n is for merging
so
and
you
n
can
by 2
see,
is because
so this you can
yes,
see. So this is a call. Okay, these are the two call, but this part actually is the additional time. So this is the main function. So this is taking order of n time, and these are simply two call.
yes, sir.
So it become a Tn equal to 2t n by 2. These are the call, and this is the additional complexity or additional step apart from the call. Okay, so that is
Yes,
the
sir.
thing. Huh.
But
So
sir, when we go to the next step,
so
sir,
if this is, we are just expanding this expression. Okay, so if we are passing n input, that n input is breaking into two calls with n by 2 n by 2. Okay, and additional steps are required n. So this n is coming as it is here. Now just solve this part, just this, take this as a one problem, t n by 2. Okay, now what will be the recurrence for this? 2 t n by, just divide this into a half again. Okay, so n by 2 divide by 2 become n by
n
4
by 4. Yes,
plus, so this
n by 2.
n value is coming as a, so this is n by 2. So
Yes,
this
sir.
one part is now breaking into two problems. So same things we are doing. So this one is breaking into two sub problem, and it is taking additionally this order n by 2. Okay, this is the additional things.
Yes, sir.
Okay, so same thing for the another part, because we have two calls. So we have solved this one. Okay, similar t n by 2. We have the another same things is coming this side. Okay, so each steps for this recurrence relation, each step, if you add the steps n by 4 plus n by 4 plus n by 4 plus n by 4, so you are getting total n again. Now so you can see this scenario, so how steps are actually moving. So your steps are uh, equal at the each level, your steps are increasing, or your steps are decreasing. So three condition will come in this type of breaking. Okay, if your steps are increasing by some factor like n square or nq like this. Okay, if steps are decreasing like n by 2 n by 4 at this type of, at the each level, or your final steps at each levels are constant. So based on these three conditions, we can calculate the complexity, and that formula is given in this recurrence tree thing. Wait. So recurrence. So based on this final number of operation at each level, so these three conditions will come. Okay, so decreasing, equal, or increasing. So now Tn. So you can consider that how we are decreasing this our recurrence relation, and what is the each term here actually. So how we are representing our recurrence relation, that is actually like this. So we are just comparing our recurrence relation in this way, like this. Okay, so Tn equal to r is just a recursive call. This value is just representing a recursive call Tn by c. So c is the divisor value in the input, plus fn. So these are the three things we can note down from our recurrence relation. So what is the R value, what is the C value, and what is the Fn value. Okay, and based on this, after that we can decide how our values are moved, total number of steps at each level. So you can see how we are calculating these steps Fn, this R into this Fn by C at each level, and finally we can just check this condition. So if our steps are decreasing, okay, each term is a constant factor smaller than previous terms. Okay, so we can directly write the complexity in this way. So Tn equal to Fn, because we have the equation like this. Suppose we have already seen in the week 2. So if suppose if you have Fn equal to n q, then plus n square plus n plus 1. So we always take this highest thing as a final complexity. We ignore the lower, the dominant part, this one. Okay, so we take this as the final complexity order of nq. So same type of sequence we are getting whenever total number of operations are decreasing at each level. So in that case, we will directly write the complexity or T of n of equal to big O Fn. Okay. So example I can give you for this. Let me explain. Binary search, or not binary search, that quick that fast select. Okay, that we can give the example here. So here, suppose if you have the recurrence like Tn equal to Tn by 2 plus n. Okay, so this recurrence relation we have already seen for fast select algorithm. So if we represent the tree for this, so this is Tn, and next level only one child is there, one call is there. So that is actually so at this steps n steps are there. The next step Tn by 2. Okay, at this step n by 2 is there. So next step T n by 4. So that step n by 4 is there. So this is reducing. You can see this order number of steps are reducing in this side. So we have this R equal to 1 here, and C equal to 2 here, and Fn equal to n here. Okay. So if our total number of steps at each levels are decreasing by some this factor. Okay, so we can directly write our complexity Tn equal to what is our Fn. Okay, Fn. So order of Fn like this. Okay, so that is order of n. So overall complexity for this recurrence relation, you can directly write order of n. Okay, so this is the example of decreasing. The next thing is if our order is equal. Okay, you can see equal is there at each level. So in that case, we pick this Fn log n. Okay, Fn into log n. So that case we have already seen for the recurrence relation for merge sort or quick sort. So like Tn equal to 2 Tn by 2 and plus n. Okay, so that is Tn and this is break into Tn by 2 and Tn by 2 calls. Okay, and this is n steps are here. So here plus n by 2 and plus n by 2, overall n. This is step. Okay, again Tn by 4, Tn by 4. Same here. Okay, Tn by 4, Tn by 4. So if you calculate all n by 4 plus 2 by 4, so you will also get n. So in this case, you can see each level's steps are equal. So we will just use Fn into log n. So this is the complexity. So Fn is this n, so n log n. Okay, so this is for equal case. So what is your Fn? Just multiply with this log n. So next step is if your complexity is increasing. Okay, so that is the one case. So in that case, how we write the complexity? So increasing case, we we take the complexity Tn equal to big O n to the power log base Cr. Okay, so this is the term we use. So how we will calculate the complexity for that? Suppose we have this T n equal to 4T n by 2. Okay, plus n. Suppose this is the recurrence relation. Now this time what is doing? So like T n is the first root. Now 4 calls are there. Okay, so that n by 4 T, oh, T n by 4, Tn by 4, Tn by 4. Okay, like this 4 calls are there, but overall first step n operations are there, but it will generate n by 4 steps. It will generate n by 4. It will generate n by 4. It will generate n by 4. Sorry, n by 2. So n by 2. So it will become a total n by 2, n by 2, 2n. Okay, if you add this, you will get 2n. Again, all call will generate to 4 4 call. Okay, like this. So each n by 4 at this step. Okay, so total 16 calls are there. So 16 into n by 4. So it will generate 4n. So now you can see this type of recurrence relation, our steps are increasing, and then 2n, then 4n, or we can write 2 to the power n, 2n. So this is our increasing. So we can just decide r equal to 4, c equal to 2, fn equal to that n. And we will write, for this type of case, we will write the complexity Tn equal to n to the power log Cr. Okay, so n to the power log, what is the value? So this log, and c is the base, so c is the 2, and this r we can write 2 to the power 2. Okay, so then it will, this 2 will come at the first place, so n 2, and this log 2 2 will become a 1, so that means n square. So for this recurrence, the complexity you can calculate by this formula if your steps are increasing. Okay, so the complexity for this recurrence relation is n square. So in this way, you can calculate the complexity for recurrence relation. Just figure out that how your steps are actually increasing or decreasing or equal at the each level, and then based on that decide which actually how you will calculate the complexity. So you can try with this each algorithms which you have seen in this week. Okay, inversion pair already merge sort is there. Otherwise, for Karasuba algorithm or integer multiplication, so the same way you can calculate the complexity. So this is the recurrence tree. So this is important for the complexity calculation. Okay. Other algorithms, yeah. So in this week, actually, some difficult or memory, you cannot remember the code or that implementation for that. This like integer multiplication, that is more mathematically things. And also that closest point, closest pair of points, okay, that is also. Generally, we not ask the questions from these tough algorithms, but yeah, these some basic things you can remember regarding this quick select. What is the worst case of quick select? What is the worst case of fast select? What is the MOM algorithms? How it works? Okay, so basic logic you can remember for this. Okay, so this is the Week-8 content. So I think this is the quiz to syllabus also. Week 5, 4, 5 to Week-8. So Week-9 will also release. After that, Week-10 is free. So just complete Week-9 also. So that is the syllabus for OPP exam Week-1 to Week-9. I'll also share some important topic for the OPP. Okay, any query? Anyone? For OPP, I am just giving you some idea that you can practice on linked list operations and graph algorithm definitely Week-4 and Week-5. So graph. So when we have the revision session, so revision session will be for quiz 2 will be conducted on the 1 week before. So when is the quiz 2? I think it's 16. So next week we will perform the
Yes, sir. Next one.
next week we will conduct the revision session. Yeah. Okay. So OPP you can practice on linked list operations and some graph algorithm definitely. So week 4 and week 5 graph algorithm and dynamic programming questions. And one problem may come from either like binary search or maybe some basic tree operation or maybe greedy algorithm. Okay, but 3 topics are approx fixed, so you can try, you can practice on that. Okay, any query, anyone, or we close? If no query. Sir, answer transcript that we have written is not released here. For quiz 1, you are asking this, huh? Okay, I'll check with team of Steam. I'm not sure. Okay, I'll check with team. Okay, if there is no query, then we can wind up the session. Thanks, everyone.
Thank you, sir.
Okay.